In this video, I will talk about the circuits in which the diodes will be connected in parallel. After that, I will show you two examples in which the diodes will be connected in parallel. When we connect two or more diodes in parallel, you have to remember that we cannot connect two dissimilar diodes in parallel. Let's say I have two silicon diodes connected in parallel like this. Let's say they are from 1N4007 family. As they are from same family, therefore their built-in potential Vk will be nearly same. Their IV characteristics curve will be nearly same. Therefore, if I want to turn on them by applying a positive voltage at this terminal and negative voltage at this terminal, you will see both of them will draw current from the source. Now see, if I have a silicon diode like this connected in parallel with a germanium diode, the characteristics of silicon diode is quite different from the germanium diode. For example, the silicon diode has a built-in potential of 0.7 volt. The germanium diode has built-in potential of 0.3 volt. Now if I write down the diode current equation, ID equal to reverse saturation current I naught exponential of V applied voltage divided by eta Vt thermal voltage minus 1. Here this eta is the ideality factor, which is equal to 1 for germanium and 2 for silicon. This implies that the IV curve of the silicon diode will be less steeper than the germanium. That means the germanium IV curve will be more steeper than the silicon. Let's say this will be silicon. Let's say this will be the IV curve of germanium. This germanium diode will draw more current than the silicon diode due to the difference in device parameters and environmental conditions. Let's say I apply a positive bias voltage here so that this terminal is positive and this terminal is negative. See, the built-in potential of the germanium is 0.3 volt and the built-in potential of silicon is 0.7 volt. Therefore, you will see the germanium diode will be in on state faster than the silicon diode. When this germanium diode will be in on state, it will maintain a voltage difference of 0.3 volt between this terminal to this terminal. So you will see most of the current from the source will be drawn by this germanium diode, and when this germanium diode will be in on state, due to the 0.3 voltage difference between this terminal to this terminal, you will see it is not possible for the silicon diode to be in on state because 0.3 volt will not turn on the silicon diode. Therefore, our silicon diode will be in off state and we have to replace the silicon diode with an open circuit. That's why we cannot connect two dissimilar diodes in parallel. You will see one of the device will end up carrying most of the current from the source because of the difference in their device parameters and environmental conditions. This is the first example of parallel diodes. Here, if the diode is in forward bias, I will replace it with a voltage source of 0.7 volt. If the diode is in reverse bias, I will replace it with an open circuit. Now see, this is our circuit structure. We have to find out the current through the resistor. I have to calculate the current through this 2 kilo ohm resistor for this given circuit. Now see, here we have total two voltage sources, 5 volt and this 10 volt. See, this is the positive terminal of the 5 volt and this is the negative terminal. So this 5 volt will try to conduct the current in this direction, that means in clockwise direction, but this 10 volt will try to conduct the current in this anti-clockwise direction, and you will see as the voltage of this 10 volt is greater than this 5 volt, therefore in the circuit the current will flow due to this 10 volt source, and in the circuit this 10 volt source will dominate over this 5 volt source. See, the positive terminal of this 5 volt source is connected with the P side of this silicon diode and N side of this silicon diode, and the negative terminal will be connected with the N side of this diode and P side of this diode. Now consider the case of 10 volt source. You will see the positive terminal of this 10 volt source will be connected with the N side of this silicon diode and this negative terminal will be connected with the P side of the silicon diode, and the positive terminal will be connected with the P side and the negative terminal will be connected with the N side of this diode. See, as in this circuit this 10 volt source will dominate over this 5 volt source, therefore this silicon diode will be in reverse bias due to the 10 volt source, and this silicon diode will be in forward bias because this 10 volt source will drive this silicon diode in forward bias. So I will replace this silicon diode with open circuit and this silicon diode with a voltage source of 0.7 volt. See here, I have removed the diode because it is an open circuit, and I will replace this diode with a voltage source of 0.7 volt. See, I have replaced this diode with a voltage source of 0.7 volt whose positive terminal is at this side and the negative terminal at this side, and in this circuit the resultant current will flow in this direction. Let's say that current is I. In this 2 kilo ohm resistor, the current will be entering from this direction, so this terminal will be positive and this terminal will be negative. Now I will calculate this current by applying KVL in this circuit. If I apply KVL in clockwise direction, applying KVL in the circuit, see, from this terminal to this terminal I will encounter this 2 kilo ohm resistor. Its negative polarity first, positive polarity later, so its voltage will be positive plus I into 2000. After that the negative terminal and positive terminal, so its voltage will be positive. After that this 0.7 volt, its negative terminal first, positive terminal later, so its voltage will be positive. But here I will get this 10 volt source, its positive terminal first, negative terminal later, so minus 10 equal to 0. From here I will get I equal to 4.3 divided by 2000, which will be equal to 2.15 milliampere. So this is the current that is flowing through this 2 kilo ohm resistor. See, this is the second example of diodes connected in parallel. Here you will see we have 3 diodes. This germanium diode will be in parallel with this silicon and this silicon diode. Now see, I have to calculate the current through this 1 kilo ohm resistor. Now look at the bias voltage. At first I have to find out the biasing condition of the diodes. Here you will see this negative terminal will be connected with the N side of diodes, and the positive terminal will be connected with the P side of the diodes. Okay, that means this applied voltage will try to turn on the diodes. But here we have another problem. See, we have germanium diode whose built-in potential is equal to 0.3 volt and silicon diodes whose built-in potential will be 0.7 volt. When we have diodes with two different built-in potentials are connected in parallel, the diode with lowest built-in potential will be turned on first. That means after applying this 10 volt source, this germanium diode will be in on state or in forward bias faster than this silicon diodes. That means it will maintain a voltage difference of 0.3 volt between this terminal and this terminal when it will be in forward bias. Now let me assume this germanium diode is in on state. Therefore, as the voltage difference between this terminal to this terminal will be fixed at 0.3 volt, you will see the 0.3 volt will not be sufficient to turn on the silicon diodes or to keep the silicon diodes in forward bias. That means our silicon diodes will not conduct any current through them. As they will not conduct any current, therefore I can replace them with open circuit. See, I have replaced the silicon diodes with open circuit because they will not conduct any current, because this germanium diode will be in forward bias faster than the silicon diodes. That means it will maintain a voltage difference of 0.3 volt across this terminal to this terminal. So now let me replace the germanium diode with a built-in potential of 0.3 volt. See, if I replace the diode with 0.3 volt, you will see it will look like this 0.3 volt. Its negative terminal will be in upward direction and positive terminal will be in downward direction. Now in the circuit you will see that current will be flowing in this direction. So let's say that current is I1K. You will see current will be entering from this direction, so this terminal should be positive and this terminal should be negative. Now to calculate the current in the circuit, I will apply KVL in the loop. So if I apply KVL from, I will encounter this 10 volt source first, its positive terminal first, negative terminal later, so its voltage will be minus 10. After that I will encounter this 1 kilo ohm, its negative terminal first, positive terminal later, so its voltage will be positive, plus I 1K into 1000. After that I will encounter this 0.3 volt source, its negative terminal first, positive terminal later, so it will be plus 0.3 equal to 0. So here I can write I current through 1 kilo ohm resistor will be equal to 9.3 divided by 1000, which will be equal to 9.3 milliampere. Okay.